Learning Target 9A. We're at the start of Unit 9. Unit 9 is all about quadratic functions and equations. In Learning Target 9A, we're going to focus on how to graph a quadratic function. By the end of this lesson, you will be able to, given the graph of a quadratic function, identify the vertex and determine if the vertex is a maximum or minimum. You'll be able to find the axis of symmetry and vertex for a quadratic equation in standard form, which is y equals ax squared plus bx plus c. And you will also be able to graph a function, a quadratic function in standard form, by finding the vertex and using the axis of symmetry. Let's start by defining what a quadratic function is. So a quadratic function is a function that can be written in the form y equals a times x squared plus bx plus c. This is what we call standard form of a quadratic. And a, b, and c are numbers here, where a cannot equal 0 because we want to make sure we have that x squared term. So a, b, and c are real numbers. Some examples of a quadratic function could be y equals 3x squared, let's say, plus 2x minus 7. That would be an example of a quadratic function. Here our a value is 3, our b value is positive 2, and our c value is negative 7. We could also have a quadratic function y equals negative 1/5, maybe x squared plus 3x. In this case, our a value is negative 1/5, and our b value is going to be positive 3, and then our c value is actually going to be 0. And that's okay if the b or the c value is 0, we just can't have the a value equaling 0. Some non-examples would be a linear function, so y equals 5x plus 1 is not a quadratic function. This is instead what we call a linear function, since the highest exponent is 1. Another example that is not a quadratic is the absolute value graph that we've seen before. So y equals the absolute value of x would not be a quadratic function. Instead, that's an absolute value graph. And the square root function is also not a quadratic function. So the key with a quadratic function is that our highest exponent is a 2, and all of our exponents are integer powers, with the highest exponent being a 2. Let's look at what the graph of a quadratic function looks like. The simplest form for a quadratic function is y equals x squared. And we're going to plot that standard graph. So I have 5 x values that we're going to plug in, and we're going to sub them each into y equals x squared. We call this our simplest form, or sometimes you could hear it referred to as the parent function, since our a value in this case is 1, which is the simplest number I can make my a, and then my b and my c values are going to be equal to 0 in this case, and that's just simplifying it down to the single x squared piece. If we sub in negative 2 squared, I'm going to take negative 2 and square it. Remember, I do need parentheses around the negative 2 since we're squaring the entire number. Negative 2 times negative 2 will give us positive 4. I can sub in negative 1 as well. Negative 1 squared will be negative 1 times negative 1, which will give us positive 1. Subbing in 0 squared, I'm going to get 0 times 0, which is still 0. 1 squared will give us 1, and then 2 squared, 2 times 2 will give us 4. We now have 5 points, and we can go ahead and graph these. So we have negative 2, 4, negative 2 to the right, and then 4 up to 4. So this one you'll notice I didn't start with a graph that has grid lines in it just so that we could really see it spaced out nicely. I have negative 1, 1. We have 0, 0. We have 1, 1. And then we have 2, 4 here. So the quadratic function follows what we call a U-shaped curve. So let me curve that a little bit better. There we go. As this curves up from there, as it keeps going. So it does curve like a U-shape. There's a couple key features on here that I want us to talk about. The first is this point 0, 0. This is what we call the vertex, and we're going to define the vertex on the next page, but our vertex on this graph is 0, 0. The other thing I want to point out is what we call an axis of symmetry. So right here, the y-axis is representing as our axis of symmetry, and that represents the line that would kind of cut this graph in half. And we can see that we have two identical halves. If I were to fold the paper over itself, I would have a mirror image on both sides. And the axis of symmetry is a line, so we want to make sure we're writing it as x equals, since it's a vertical line, and that would be at x equals 0. The other important thing that we're going to talk about in this unit is, well, what is the domain and the range for this graph? So remember, our domain is our set of input values. So those are our x values. What can I input into here? Whereas our range is our set of output values. So let's start with the input values. We were able to input negative numbers and square them. We were able to input 0 and square 0. And we were able to input positive numbers and square those. Now, though we just did 5 points here, I could have taken negative 10, negative 100, negative 52. I could have taken any negative number and still squared it. I could also do the same thing with any positive number. I can also square any fraction that I have. I can square a decimal that I have. So in this case, because there's no restriction to what we can input into the x squared, our domain here is what we call all real numbers. On a graph, what that looks like is that the graph when I'm looking at the x-axis here, I could plug in all of these x values as I continue on to the right, and I would get more points up here. They'd grow bigger and bigger since I'm squaring each one of those. Likewise, on the negative x-axis, I could also plug in values as I continue on the negative x-axis, and that graph will keep growing bigger and bigger. The range, remember, is our set of outputs, so it's what we get out of these numbers. Well, think about this. When we have the function y equals x squared, what's always true no matter what number I plug in? What's going to happen when I square that number? Anytime I plug a number in and I square it, that number is always going to come out positive. And so because when I plug stuff into y equals x squared, the x squared piece always makes it greater than or equal to 0. Our range then is going to be y is greater than or equal to 0. Since no matter what I plug in for my x, when I square it, I will either have a positive number, or if we subbed in 0 like we saw here, we will end up with 0. So our range here is not all real numbers, it's strictly all the positive values for y and equal to 0 as well. The reason here that I used a y in my inequality is because my range is dealing with that variable for our y, so I want to make sure I include the variable that the range is associated with. Another way that you could write this is we could write this in interval notation, and I'd have a bracket at 0, since I'm including 0, comma, infinity with an open parenthesis. On the graph, we can see this because when we look at the y-axis, we'll notice that our lowest point here, which is at our vertex of 0, 0, there's nothing below this point. Everything on the graph is above it, so all the y values are dealing with the positive y-axis, nothing down here. One thing I do want to say though, as we change this function, as we make it more complicated, remember this is just our simplest form of this graph, so as we change this and make this more complicated, our range is going to change depending on where the vertex ends up moving to. And in this video, we're going to look through some examples on how to find that vertex and then see where it moves to, and then we'll talk about the domain and the range from there. So this is only true for our simplest form, y equals x squared. Okay, let's define what a vertex is. So I'd said this before, but the graph is what we call a U-shaped curve. So our graph of a quadratic function is a U-shaped curve, and we call that a parabola. So this graph does have a special name. It's called a parabola. You could also call it the graph of a quadratic function. Those terms are interchangeable. The vertex that we talked about at 0, 0 up here is the coordinate pair that represents the highest or the lowest point on the parabola. So in this example that we graphed, our vertex here is the lowest point, and that's what we would call a minimum. If this graph was flipped upside down and we had the vertex at the highest point, we would call that a maximum. So if the vertex is the highest point, we call this a maximum. So that would be if the U shape was facing upside down, then I'd have a maximum up here. Versus if I have the vertex as the lowest point, that's what we call a minimum. So on our example above, that graph would have a minimum at 0, 0, since our vertex was the lowest point. The other thing that we talked about up there was that axis of symmetry line. So this was that red dotted line. So the axis of symmetry is a vertical line that divides the parabola into two matching halves. And that axis of symmetry is going to help us graph. So when I'm looking at this, remember we could kind of fold the paper over itself and I have a mirror image on either side. And the way this can help us graph is if I find points on one side of the vertex, I can just flip them to the other side without having to do any new work. So this axis of symmetry will help us kind of simplify our process and only have to do half the work then, and then flip them over the axis of symmetry to get the other matching points on the other side. I do want to point out that we did need to graph 5 points on this graph so that we can see the full shape. So as we're doing examples, we're going to want to make sure we have at least 5 points on those graphs. The last thing that we have to define has to go back to doing with the vertex. So remember how we have the maximum and the minimum cases up here. So the maximum, I said, is when the graph's facing upside down. Well, it would be really nice to know if the graph's facing upside down or right side up to begin with, and we actually can. So by looking at the equation for the quadratic function, we can determine if the vertex will be a maximum or minimum on the graph. And we can do that without solving anything, we just have to identify one key thing. And that key value that we have to identify is a. So if a is a positive number, so remember a is the number in front of our x squared there. If that's a positive number, then the parabola opens upward, meaning that graph would be facing up like a smiley face, you could say. So if my a is positive, my graph faces upwards like a smiley face. But in this case, I actually have my vertex down here then. So this would be a minimum on my vertex then, since it's the lowest point on our graph. On the flip side, if a is less than 0, remember a is in front of our x squared. If that's less than 0, then the parabola opens downward. So the parabola is opening upside down, that'd be like a frowny face. And in this case, our vertex is going to be a maximum since it's the highest point on our graph. And that's going to be helpful as we move on. I don't have to solve anything. All I have to do is look at the equation. And if my leading coefficient, or my a value, which is the number in front of the x squared, is positive, then my graph is facing right side up like a smiley face, which means my vertex is then a minimum. And I think it is really helpful to draw the graph because it's a little weird to say that if a is bigger than 0, I have a minimum. Intuitively, we would think, well, if a is positive, shouldn't that be a larger value? But it's the fact that since a is positive, the graph is facing upward, which means that the vertex is then the lowest point, so the vertex is a minimum. This is why drawing kind of a little sketch can be helpful. On the flip side, if a is negative, then my graph is opening downwards, so I have this upside down U, so like a sad face, my vertex then would be a maximum. We're going to do a couple examples where we're given the graph and we want to find all this information that we've talked about. So here's our first 2 examples. They say identify the vertex and determine if the vertex is a max or a minimum, then find the axis of symmetry, domain, and the range. So let's look at our first graph here. Here I have a graph that is facing downward, so I have this U shape that is opening downwards. My vertex then would be our highest point. What coordinate pair is that vertex at? So our vertex on this graph would be up here since that's our highest point, and that coordinate pair would be 2 to the right, so 2, 3 up. So my vertex then would be at 2, 3. We've established that it's a maximum since that's the highest point. The axis of symmetry, remember, is the vertical line that runs through the vertex. Vertical lines we know are x equals, and it's running through 2, 3, so the axis of symmetry then has to be at x equals 2, and these numbers here, the x coordinate of the vertex will always match what the axis of symmetry is equal to since it's running through that point. The domain and the range we talked about when we defined the parent function. So our domain of any quadratic function is going to be what we call all real numbers. I'm going to shorthand that with ARN to represent all real numbers, and that will be true for all quadratic functions. So our domain being all all real numbers is true for all quadratic functions. Our range, though, is what's going to change. So our range is based off of two things. It's based off of where the vertex is located, and if that vertex is a maximum or a minimum. Let's scroll back up to this basic graph that we looked at up here. Up here, we said that our range was y is greater than or equal to 0. The reason it was greater than or equal to is because my vertex here was the lowest point. So everything had to be above it. The reason it matched with 0 is because 0 was the y component of my vertex. So that was the lowest point down here on the y-axis that we moved. That thought process is going to work for every single problem when we talk about range. We're going to have to figure out if the vertex is first a max or a min, and then we'll have to find the numerical value of the vertex, and that will help us get the range. So for this case, my range always deals with y. Because I have a maximum now, y is going to be less than or equal to, since the graph is facing down. And in this case, it's less than or equal to 3, since 3 is the highest y value that we can move on our graph up here. So the less than or equal to is coming from the maximum, because this is the highest point now on my graph. And the 3 is coming from the 3 in the vertex in the y spot, since that is the highest point that we can reach. Why don't you guys pause the video and try example 2 on your own first? Okay, let's check example 2. So in this case, my vertex is actually the lowest point, so my vertex is a minimum now. When I count where the vertex is at, it looks like it's at 1, 2, 3, comma, negative 1, 2, 3, 4. So 3, comma, negative 4 will be our vertex. Remember, the axis of symmetry always matches the x coordinate of our vertex. So it's the line running through there. So it'll be x equals, since it's a vertical line, and it'll be x equals 3, since that's the x component of the vertex. Our domain for any quadratic function is going to be all real numbers. So that will always be true for any quadratic function. And our range in this case, since I have a minimum, our range is y is greater than or equal to negative 4, since that's the lowest spot that we went down on our y-axis. How do we find the vertex if we don't have a graph? So in these two examples, we were given a graph, and so we can identify the vertex from the graph and then count to that spot on the graph by counting over in the coordinates. Well, that's not always going to be true. Sometimes we're going to need to algebraically compute our vertex and our axis of symmetry. If we have a quadratic equation in standard form, which is y equals ax squared plus bx plus c, then the graph of that function has a vertex at this really funky coordinate pair. And I know that this looks very messy, and we're going to talk through this a lot. But the x coordinate here is computed by computing negative b over 2a, where our a value is the number in front of the x squared, and the b value is the number in front of the x term. So we're going to first have to identify what is our a and our b so that we can compute this. To get the vertex, we sub those values into negative b over 2a. That will be the x component. Of course, we're going to want to simplify that down as much as possible. Then to get the y component, well, I would plug the x back into the function. So this f of negative b over 2a represents us taking the value that we get in the x component and subbing it back into this entire function that we started with, whatever our original standard form was. The axis of symmetry is going to be at x equals negative b over 2a, since remember, these two values are always matching. The axis of symmetry number equals the x coordinate in the vertex. Let's just jump right into some examples so that we can see how this equation gets used. So in examples 3 and 4, it says find the vertex, determine if the vertex is a maximum or minimum, then find the axis of symmetry, domain, and the range. That's a lot that we have to do here. So I'm going to start with the basics. I got to figure out what a is, what my b is, and what my c value is. So the equation we're starting with says f of x equals negative x squared plus 4x minus 3. So why don't you guys pause the video right now and decide what the A value is, the B value, and the C value is. So for this function, our A value is going to be -1, since it's the number in front of the x squared. Our B value is going to be +4, so we want to make sure we take the sign with it. And then our C value, I'll do that in green, is going to be -3. And again, I want to make sure I take the sign with that. Now that we have these three values, I'm going to start by computing that -b/2a portion of the vertex. To do this, I'm going to sub them in. So for B, I'm subbing in 4. So I end up with -4 as the original negative sign in the formula, over 2 times our A value is going to be -1. From here, we can use order of operations and simplify this down. So we get -4 over -2, which gives us a +2 value. This right there is going to be the x-coordinate of the vertex, since this is our -b/2a, and that goes in the spot of the x component of the vertex. So I'm going to start filling in what we know then. So that means our x component of our vertex is going to be 2, something. That also tells me what my axis of symmetry is. So my axis of symmetry matches that value, so it will be x = 2. Now we're going to find the y component of the vertex. So this was getting the x component. To get the y component, I'm going to plug that back into my original problem. So I'm going to compute f of -b/2a. Well, -b/2a we just found was going to be equal to 2. So really, what I want to compute in this problem is what is f of 2. Remember, what function notation tells us is anywhere there's an x, I want to plug in now my new value, so I'm going to plug in a 2. I end up with negative times 2 squared instead of the x squared, plus 4 times 2 minus the 3. From here, we have to make sure we use order of operations correctly. In the first term, I am not squaring the negative sign since the negative is in front. So 2 squared is going to be 4. So I end up with -4 then, since the negative sign stays, plus 8 minus 3. Simplifying this down, we end up with 4 minus 3, which equals +1. And what this 1 is representing is the y component, or the y coordinate of that vertex. So going back to my list of answers over here, I can then put a 1 in the spot of my y component in my vertex. So to recap this, although this formula is very messy for finding the vertex, it's really all I have to do is find the x component, and then once I have that x value, I then sub that back into the original problem I'm given to find the y value. And hopefully that's making some sense. That's how we always find y values. We solve an x value, and then I sub that in to get my y value. Because remember, x is our independent variable, and y depends on what the x value is. So to get the y value, we would always have to take an x and plug it back in. To get this x value, it's the formula -b/2a. So once we've identified our a, b, and our c, I can sub them in. So I'd end up with -4 over 2 times -1 for this example. Simplifying that down, I ended up with -4 over -2, which equals +2. This then is the x component of the vertex. It is also the value that goes into my axis of symmetry, since the axis of symmetry runs through the vertex. I can then use this value to get the y value by taking the 2 and plugging it back into my original function. That's this f of -b/2a. That's the same thing as finding f of 2, but we know from function notation that f of 2 just means that I plug 2 in for all the x's. Using order of operations, I can simplify that down and I end up with +1, and that's representing my y coordinate of the vertex. The last 3 things left are the question of max or min, domain, and range. What do you guys think? Is this going to have a maximum or a minimum? So, in this case, to figure out our max or min, we have to look at that a value. Our a value is -1, which means that it's less than 0. So that means that the graph is opening downward. So the graph is facing down since that is a negative a value. So in this case, I actually have a maximum then, since my vertex would be my highest point. Our domain, we know for any quadratic function, is going to be all real numbers. And our range is going to be based off of if I have a max or min and then my vertex. Because I have a maximum, it means my vertex is the highest point. So my range has to be a less than or equal to. And in this case, it's going to be y is less than or equal to 1, since 1 is the y component from the vertex. So again, to get that range, it's a less than or equal to because I have a maximum. So on my graph, the vertex is the highest point, everything's below it. And then the 1 is coming from my y component of my vertex. Let's look at our second example here. So our second example says y equals 3x squared minus 6x plus 1. Why don't you guys pause the video and find your a, your b, your c values, and then compute what negative b over 2a is equal to, and then we'll check that together. To check this, our a value is going to be positive 3, our b value is negative 6, and our c value is going to be equal to positive 1 by taking them from that standard form equation. That tells me that negative b over 2a is going to be equal to negative 6. So I have the negative sign on the outside as part of the formula. And then in this case, b is actually a negative number, so I end up with 2 negatives all over 2 times 3, since that's my a value. Simplifying, I end up with 6 on top over 6 on the bottom. So I get a value for negative b over 2a to be equal to positive 1. What information does this help us start to find now? So what this helps us start to find is the fact that our vertex is going to be 1 comma some number. So that's the x component of my vertex. That is also the value for my axis of symmetry, making sure, of course, that I have the x equals since it's representing a line. So x equals 1, and my vertex is going to be 1 comma some number. Now from here, we want to compute f of negative b over 2a. To find that, I'm going to sub in what negative b over 2a is equal to, which is 1. What f of 1 means is that anywhere there's an x up here, I'm subbing in 1 in place of that. So I end up with 3 times 1 squared minus 6 times 1 plus 1. The plus 1 that was already there. Simplifying this down, I do exponents first. 1 squared is 1, so I get 3 times 1 minus 6 plus 1. We end up with 3 minus 6 plus 1, which would be negative 2 plus 1, or I'm sorry, negative 3 plus 1, which will give us negative 2. That negative 2 is representing the y component of my vertex. It will also come into play in my range. So I know that my range is going to be y, either less than or equal to or greater than or equal to, I'm not sure yet, and then I'll be comparing that to negative 2, since the negative 2 is in the y spot of the vertex. The next thing let's find is our max or our min. What do you guys think? Does this graph has a maximum or a minimum? So in this case, our a value is 3, which is a positive number, so the graph is facing upwards like a smiley face, so I actually have a minimum this time. Our domain we know is all real numbers, just like that's true for any quadratic function. And then for our range, what type of inequality will we have on our range then? Since we have a minimum this time, our range is going to have a greater than or equal to, since our vertex is the lowest point. So that means our range is y is greater than or equal to the negative 2, since all the other points are above on that graph. We're going to continue practicing finding this information on the next 2 problems, but we're also going to add in about graphing on the next 2 problems. So example 5 says find the vertex, determine if the vertex is a max or min, find the axis of symmetry, domain, and the range. We've been doing that. The next step is we're also going to use that information to help us graph. So I first want to find all this information, and that will help us actually get a graph without having to do any new additional, having to do much more additional work. So why don't you guys pause the video, list your A, your B, and your C values, and then find your vertex, and we'll check it together. In this case, our A value is positive 1, our B value is negative 6, and our C value is positive 4. To get my vertex, I first need to compute negative B over 2A. So I get negative 6 over 2 times 1, which will give me 6 over 2, which will give me 3. That tells me that my vertex is going to be at 3 comma something, and that my axis of symmetry will be at x equals 3. As you guys have seen in the prior examples, as soon as I find one piece of information, I start to fill it in on this list of answers. And I do that so that I don't get overwhelmed at the end, and I've already started identifying features that are going on here. The next thing we need to compute is f of negative b over 2a, which in this example will be f of 3. To find f of 3, remember I plug in 3 everywhere I have an x. Why don't you guys pause the video and simplify that on your own first. So here we're going to get 3 squared minus 6 times 3 plus 4. So we end up with 9 minus 18 plus 4, which would give us negative 9 plus 4. So we'll end up with negative 5 then. That will be the value then for my vertex, or for the y component of my vertex. So I'm at 3 comma negative 5. The next piece let's address is the maximum or the minimum. Why don't you guys pause the video, determine if you have a max or min, find the domain, and find the range as well. In this example, since our a value is positive, the graph is facing upward like a smiley face, so our vertex then is going to be a minimum. Our domain, like in any problem, is going to be all real numbers, or I should say for any quadratic function is all real numbers. And our range is always going to be comparing y to the y component of the vertex. So I'll have the y and the negative 5. Since this is a minimum, then our range is greater than or equal to negative 5, since everything is above that vertex on the graph. Since the vertex in this case is the lowest point, since it's a minimum. Let's start plotting some things. So right now I know what my vertex is. So I can go over 3 and then down to negative 5, 2, 3, 4, 5, and I'm going to put a point there. So I have my vertex. I also know that I have this axis of symmetry that's going to run through that vertex. And how that's going to help me is if I find information on one side of the graph, so let's say if I find what's going on the left side of the graph, then I can take the mirror image to figure out what's going on the right side of the graph. And we're going to take advantage of this. I also want to keep in mind that I have a minimum here, so all of my points that I get should be above this vertex. So this 3 comma negative 5 is the lowest point I can go on this graph. To find more points, I need at least 2 points on the left, and then that can get me 2 points on the right. So on the left side, I want to pick values that are easy to sub in. One of those values that's always going to be easy to sub in is going to be x equals 0. Now I don't have to use x equals 0, but I do have to pick 2 points on the left side. And this is a choice that we get to make. You can pick any 2 points that are to the left of 3. So I could pick 0, I could pick 1, I could pick 2, I could pick negative 1, I could pick negative 2, and keep going. Personally, I'm going to keep them as close to the vertex as I can, and I want to pick values that are nice and easy to sub in. And 0 happens to be one of those. So when I sub in x equals 0, I'm putting 0 in place of all the x's. So we get 0 squared minus 6 times 0 plus 4. Simplifying this down, 0 squared is 0, 6 times 0 is 0, so I end up really with just positive 4. What that's giving me then is the coordinate pair 0, 4, and I can plot that on my graph. So I don't go right or left, but I go up 1, 2, 3, and 4, and I'm going to put a dot right there. The other thing that this can help me get is the mirror image that's going to be somewhere over here. But what I have to figure out is what that y value is going to be. So I'm going to label this 0, 4. I know that the y component is going to be 4, but the x component is going to depend on how far 0, 4 is away from my axis of symmetry. So when I look at this, to get from 0, 4 to the axis of symmetry, how many units is this that I would be moving? So we would be moving 1, 2, 3 units. So this is 3 units between 0, 4 and our axis of symmetry, which is x equals 3. So that means I have to move 3 more units over here when I get the mirror image. So I'm at 1, 2, 3, and then my dot would go right there. On the x-axis, that's at 6 then. So this would be at the point 6, 4 then. Okay. I'm going to erase our little unit markers there since I only need the points on the graph. Okay, we do need to find one more point that's to the left. So I'm going to go ahead and pick the next nicest value, which would be x equals 1. When we sub that in, we get 1 squared minus 6 times 1 plus 4. 1 squared is 1. I get 1 minus 6 plus 4. That ends up giving me negative 5 plus 4, which equals negative 1. So my next coordinate pair that I have is 1, negative 1. So I can go to the graph, go 1 to the right, and go 1 down, and that will be my next point. I'm going to label it over here, 1, negative 1, because there's really not enough space. Again, I have to find the mirror image. So I have to think about how many units did I move from the axis of symmetry to that point. So how many units is there between 1, negative 1 and the axis of symmetry at x equals 3? This time there's only 2 units. Since I moved from 1 to 3, that difference is 2. So I have to move 2 units again, which will put me this time at 5 then. So I'm going to erase those unit markers. I'm actually going to switch back to the blue. So that point right there would be at 5, negative 1. Now this is enough to sketch my graph. Remember, we are getting a U-shaped, so this graph should be curving as it keeps going up. This is also a function, so the graph should be passing the vertical line test as we keep going. Whoops, that got a little curvy. Personally, for me, the right side is easier to draw because I'm right-handed. I think the left side is a little bit trickier. So we got most of this information already to begin with. We knew what our vertex was. We knew that we had this axis of symmetry. We also knew that we had a minimum, which meant all of the points that we should be finding should be above. So if one of these points I ended up plotting, and let's say I got 1, negative 10, then something would have been wrong because there's no way that I can have a point that's lower than my vertex if my vertex is a minimum. So that's a way to kind of check your work as you're going through this. To find the additional points, I just picked 2 values in this case that were to the left. And I tend to use 0 and 1 a lot just because they're nice values to sub in. Once I found those values, I can find the mirror image by figuring out how far the point is that I found from the axis of symmetry, and then moving that equal amount of spaces on the other side of the axis of symmetry as well. Let's look at our last example. Why don't you guys pause the video right now and find the vertex, determine if it's a max or min, find the axis of symmetry, the domain, and the range on your own first. Okay, let's check all that info. So in this case, our A value is negative 2, our B value is negative 8, and our C value is negative 7. So when we're computing negative B over 2A, that means I get negative 8 over 2 times negative 2. Simplifying down, we get 8 over negative 4, which gives us a negative 2 then. This will be the value for the x component of my vertex. It will also be my axis of symmetry. So I'll get x equals negative 2. Again, really make sure that you are writing the x equals on the axis of symmetry, otherwise your answer would not be fully correct. To finish off the vertex, I need to compute the y value that goes with that. So I need to find f of negative b over 2a. We know that negative b over 2a equals negative 2, so I really just need to find f of negative 2. Again, to find that, means I'm subbing negative 2 in for all the x's in my original equation. So I get negative 2 times negative 2 squared minus 8 times negative 2 minus 7. From here, I gotta simplify, making sure I'm using order of operations correctly. Exponents come first, so the negative 2 in front is gonna stay in front. Negative 2 squared is positive 4. Negative 8 times negative 2 is gonna be plus 16. And then I still have the negative 7. Simplifying, I get negative 8 plus 16 minus 7. So I end up with 8 minus 7, which is going to give me positive 1 then. So that will be the value in the y spot of my vertex. To determine if I have a max or a min, I look at the a value. Since our a value is equal to -2, that graph should be facing downward then, so my vertex should be a maximum. Our domain, like for any quadratic function, is all real numbers, but our range is going to be restricted. So in this case, because I have a maximum, y is going to be less than or equal to, the value will be 1 since that's the value for the y spot in my vertex. I'm going to go ahead and graph that information so far. So I'm at -2, +1. There's my vertex. I also know that I have an axis of symmetry running through x equals -2, which will be helpful when I go to graph. Now I might have to erase some of this work down here because I think the graph's going to intersect it. We'll worry about that when that happens. The next thing I need to figure out is some more point values. So again, I have the choice. I could pick 2 points on the left, get the mirror image for the right, or I could pick 2 points on the right, get the mirror image on the left. Personally, what I'm looking at is I want to pick values that are easier to simplify. One of those values is always going to be x equals 0. So I'm going to go ahead and plug in 0 for x and see what we get out for y. When we do that, we get -2 times 0 squared minus 8 times 0 minus 7. All of that zeroing out, and I end up just getting -7. So my first coordinate pair we get then is 0, -7. So that's going to be way down here. 1, 2, 3, 4, 5, 6, and 7. So I probably am going to need to erase stuff over here. So let's do this. I wonder if I can just move this information. I think I can. Sweet. I'm going to move that over there for us so it's out of our way. Couple things that did get left out was the negative signs, so let me just put those back because we did have those negative signs. Oops. So I just moved the stuff over so that I have enough space to now graph. Now that we have 0, -7, I can use the mirror image on the left side over here to get the point at something, -7. I have to figure out how far I moved. So how far did we move from the axis of symmetry, which is at x equals -2, to the coordinate pair 0, -7? How far did we move there? We moved 2 units, which means I need to move 2 units now to the left, which would put me at -4. So my other point will be at -4, -7 then. The next value I'm going to figure out is what's happening at x equals -1. Now I could use +1 like we did in the last example, but that's going to give me an even bigger value down here since this graph keeps going. So to simplify the fact that I might run out of space down here, I'm going to instead pick x equals -1, which is in between the vertex and the other point that we already found. When I pick -1, I sub -1 in for all the x's. So I get -2 times -1 squared minus 8 times -1 minus 7. Using order of operations correctly, we have the exponents first. So -1 squared is +1. I get +8 minus 7. So we end up with -2 plus 8 minus 7, which for us will simplify down to be -1 then. So the next point that we have is going to be -1, -1. So left 1 and down 1 will get me that point. I have to get the mirror image on the other side. So in this case, we only moved 1 unit away from the axis of symmetry to that point. So I just have to move 1 unit on the left side, which will put me at the coordinate pair -3, -1. Let me go ahead and label this point as well. Erasing those kind of those markers to help us find it. Let me put the point back. -1, -1. We now have enough to create this shape because I have 2 points on the left of the vertex and 2 points on the right. So when I go to create this shape, now this is a steeper parabola as we're seeing. So it's coming down to the left, not doing that on the right, coming down on the right, and then as it keeps going. So this is creating that U-shaped curve that we are getting. Okay, so on here it's really helpful to first find all that key information. Vertex, axis of symmetry, determine if the vertex is a max or min, find your domain and your range. That helps you start creating the graph. Then from here, if I pick 2 points on one side, I can then use the axis of symmetry to get the mirror image on the other side. This is the end of learning target 9A, where we focused on how I graph quadratic functions. The rest of this unit is going to shift and focus on how do we solve quadratic equations, and we will go through all the different methods that there are to solve these quadratic